Hey everyone, and welcome to this Masterclass Explainer. Today we're taking a seriously fascinating journey into the world of earthquake-resistant design and construction, looking specifically at the absolute masterclass techniques pioneered in Japan. Now, if you are an aspiring construction management professional, this explainer is built exactly for you. We're going to look at how high-level, brilliant architectural concepts actually translate into rigorous, on-the-ground project management realities. Because at the end of the day, it's not just about what a building looks like. It's about how it's built to survive. Here is a quick look at our syllabus for today. We'll move from the layers of earthquake safety and 3 core seismic strategies, straight into the gritty construction management reality, geotechnical risks, and finally, wrap up with some global lessons in resilience. All right, let's jump right into Section 1, the layers of earthquake safety. We need to start with the macro-level view of how Japan actually approaches earthquake resilience.
You know, there is this massive misconception out there that earthquake safety just means building an indestructible bunker. But in reality, safety is a highly layered project management and engineering problem. It's a whole ecosystem. It starts with analyzing the hazard and the site, moves into incredibly strict building codes, selects a specific structural system, focuses intensely on detailing, and then finally incorporates ongoing operations and recovery plans. The goal here is absolutely not to make a building that never moves. I mean, that's impossible anyway. The true goal of Japanese technical codes is controlled movement, damage limitation, and above all else, life safety.
Moving on to Section 2, 3 core seismic strategies. It's time to escalate our terminology a bit and look at the actual physical methods these buildings use to handle those massive earthquake forces. Japan essentially relies on 3 broad categories of earthquake strategies. First up, we have taishin, or seismic resistance. This is basically making the structure strong and ductile enough to just tank the shaking. Then there's seishin, which is response control and damping. With this one, we actually let the building move, but we add devices like massive shock absorbers that eat up the energy. And lastly, menshin, or base isolation. This is where the building essentially rides on isolators, physically separating the structure from the violent shaking of the ground below. So, as future construction managers, why does all that matter to you? Well, because each of these strategies demands a totally different quality control and on-site management technique. If your project uses taishin, your day-to-day focus on site is going to be checking extreme rebar congestion and ensuring absolutely perfect concrete placement. If you're building a seishin structure, you suddenly have to manage architectural space to ensure those dampers can actually move, and more importantly, be accessed for maintenance years down the line. And for menshin base isolation, you are out there meticulously managing isolation moats and flexible utility loops so the building can actually sway back and forth without snapping its own power lines.
Okay, Section 3, the construction management reality. We are going deep into professional territory now.
I want you to really think about this for a second. How is seismic intent actually carried from the design phase into shop drawings, site layout, inspection, and closeout? Because let's be real, the most brilliant, Nobel Prize-winning seismic devices mean absolutely nothing if they aren't installed correctly. Without intense, layered project management, a world-class design is really just a nice idea on paper. Let's walk through this incredibly unforgiving chain of performance. It flows from hazard assumptions, to analysis, to detailing, to fabrication and site installation, and finally to inspection and maintenance. For you as a CM, the scary reality is that a failure at any single step in the field ruins the entire design intent. Think about it. If just one bearing is installed off tolerance during Step 4, that multi-million-dollar system from Step 3, completely compromised. And right here, this is where you earn your paycheck. There are critical hidden details requiring extreme QA/QC before cover-up. We're talking rebar placement, confinement ties, anchor bolt positioning, connection welding, device orientation. The core motif of seismic construction is that quality matters immensely because these life-saving elements are permanently hidden after construction. You can't just go back and fix a bad weld once it's encased in concrete or hidden behind drywall. You just can't. You have to catch it right then and there. But it doesn't stop at installation. Modern practice puts a huge emphasis on severe verification. Verifying the performance of isolation and response control components is a massive administrative and logistical responsibility. Doing full-scale dynamic testing of large isolation devices isn't just some engineering footnote. For the CM team, managing that product testing and certification is a critical part of project risk management.
Right, Section 4, geotechnical and infrastructure risks. Let's broaden our lens a bit and look at the wider infrastructure.
Because here is the hard truth. You can build a theoretically perfect structure, but it can absolutely still fail if the ground beneath it literally turns to liquid, or if the utilities connecting it are severed. As a CM, you're constantly responding to hazards. Soft ground means you're planning deep foundations and soil cement walls. You're tackling underground utility risks by ensuring flexible joints and automatic shutoff valves are perfectly installed. These geotechnical risks have to be integrated super early in your project delivery to ensure the building actually functions and recovers rapidly after a quake.
Take Japan's famous Shinkansen, the bullet train, as the ultimate example of this. True resilience here is a fully integrated system. It's not just having strong concrete viaducts, it's structural capacity combined with earthquake detection seismometers, automatic train controls, and rapid inspection protocols. The whole shebang has to work perfectly together.
I really want to hammer this takeaway home. Site context and infrastructure redundancy are just as important as the building's skeleton. A state-of-the-art hospital might survive the shaking flawlessly, but the project is an operational failure if the access roads collapse or the water supply is permanently cut off. The scope of your safety management extends way beyond your property line. Which brings us to our final part, Section 5, Global Lessons in Resilience. Let's connect all these highly technical practices to real-world outcomes. To see how these strategies actually adapt to unique real-world constraints, just compare the Tokyo Skytree to the National Museum of Western Art. The Skytree uses a central column, called a shimbashira, along with massive oil dampers to control extreme sway. It's communicating high-tech safety through a very traditional, familiar cultural concept. Meanwhile, the museum was retrofitted with base isolation. Why? Well, they had to protect life, but they also had to entirely preserve the historic Le Corbusier architectural character without adding any ugly visible bracing. Different goals, different strategies, and totally different CM challenges. This brings us to what I consider the absolute climax of this masterclass. Consider this crucial takeaway. The most important lesson for global construction managers is that local risk fundamentally changes the meaning of quality.
Let me expand on that just a bit. Take a standard construction detail, say a welded steel joint. That weld carries far more weight in a high seismic zone like Japan compared to a low seismic region. In a low-risk area, quality might just mean staying under budget, building it fast, or making it look pretty, but in Japan, that exact same detail is a strict, non-negotiable guarantee of life safety, business continuity, cultural preservation, and public confidence in the wake of a massive disaster.
So I want to leave you with a provocative thought to carry into your careers. Based on the layers of safety we've uncovered today, how does this specific risk in your local region change the definition of quality on your own projects? Think about those hidden details you'll be overseeing. Thank you so much for joining me in this explainer, and I hope you take these lessons and go out there and build something truly resilient.